Last episode, we simplified the network into one pipe. Today, we try to fill it and see what happened. You'll see. There are only three ways a flow can be limited. Packets tell the secrets, Wireshark listens, and you see the truth. I'm Tai Fung, and welcome back to my network analysis class. Now let's fill the pipe and analyze how a transfer behaves. To start, for simplicity, we'll assume that the TCP endpoints, the sender and the receiver, don't impose any limitations themselves, and that there are no transmission errors. We'll bring those scenarios into the model in later episodes. With that simplification, we can focus on how the network behaves. We can model this dynamic process. The sending rate starts low, increases, approaches the bottleneck bandwidth, fills the buffer, and eventually causes loss. This whole process can be abstracted into a simplified network congestion model. No matter how complex the real network is, we can use this model to describe the key behavioral changes. In this model graph, the vertical axis includes metrics like RTT, bytes in flight, send rate, and delivery rate. The horizontal axis is time. This model involves core parameters you can see in Wireshark. Send rate, how fast the sender transmits data. Delivery rate, the speed at which the network actually delivers data. Bytes in flight, the amount of data transmitted by the sender that has not yet been cumulatively acknowledged. Round-trip time, RTT, the time it takes for a packet to travel from the sender to the receiver and back again. Buffer size, the amount of memory the bottleneck device, like a router or switch, allocates to store packets while waiting to transmit them. Queuing delay, the time a packet spends waiting in the buffer before being transmitted. The maximum queuing time a packet can wait in a buffer is determined by buffer size and bottleneck bandwidth. Bottleneck bandwidth, the maximum transmission rate of the slowest link along the network path. BDP, bandwidth delay product, the product of bottleneck bandwidth and RTT. It represents the amount of data that can be in flight in the network to fill the pipe. The dynamics of transmission are revealed through the interaction of these parameters. There are two critical threshold lines on the time axis. The first is the BDP line. When the bytes in flight hits the BDP, it means you've just filled the pipe perfectly, but haven't started causing queues yet. The second is the BDP plus buffer size line. When the bytes in flight exceeds this, you've not only filled the pipe, but also completely filled the buffer. Past this point, packet loss becomes inevitable in tail-drop networks. These lines divide the whole process into three phases. 1. Application limited phase. The application itself isn't sending enough data to utilize the full available bandwidth. 2. Bandwidth limited phase. The send rate exceeds the available bandwidth. Now the bandwidth itself becomes the limiting factor, putting a ceiling on the delivery rate. 3. Buffer limited phase. Pushing the rate even higher uses up the entire buffer, triggering packet loss. The total size of BDP plus buffer size limits any further growth of CWND and bytes in flight. Right when the send rate first hits the bottleneck bandwidth, the RTT is roughly equal to the base RTT. The send rate is fully utilizing the bandwidth, but no queue has built up in the buffer yet, so the delay is minimal. This point was identified back in 1979 by Leonard Kleinrock as the optimum operating point for network congestion control. An algorithm that could sense and maintain this rate would be perfect. At this spot, you get maximum bandwidth utilization, minimum delay, and zero packet loss. It's ideal for both a single connection and the network as a whole. However, if the transmission keeps accelerating, the buffer starts to queue, RTT begins to rise, and it continues until the buffer is full and packets are dropped. This point is where classic loss-based congestion control algorithms like Reno and Cubic typically operate. For performance analysis and troubleshooting, this network congestion model is invaluable. It moves us away from guessing and relying on vague experience. Instead, it gives us a repeatable, verifiable method that anyone can learn and use. Simply put, the model reveals the characteristics of each transmission phase with crystal clear, deterministic signals. By identifying these signals, we can make precise, accurate judgments. We're no longer chasing shadows or trying to fit evidence to a preconceived conclusion. This model lets us strike at the heart of the problem. Before we can truly use it, we must dive deep to see the characteristics of each phase. Let's walk through that process again, but this time with more precision. First, it hits the bottleneck bandwidth limit. If it keeps sending, the excess data enters the buffer, RTT starts to rise. If it continues, the buffer overflows and packets are dropped. There is a critical point in this process. When the send rate equals the available bandwidth, three conditions are met simultaneously. Bytes in flight equals the BDP. Send rate equals the available bandwidth. RTT equals base RTT. This is the ideal state. Bandwidth is fully utilized with no queuing, no loss, and minimum delay. Before this ideal point, the network is in the application limited phase. Its characteristics are clear. Bytes in flight is less than BDP. RTT is at its base value and stays there, even if bytes in flight changes. Send rate equals delivery rate, which is less than the available bandwidth. The throughput limit is the send rate, not the network. No loss, no queuing, no congestion. If the send rate continues to rise, we enter the bandwidth limited phase. Its features are just as clear. Bytes in flight is between BDP and BDP buffer. RTT increases above base RTT and varies with bytes in flight. Send rate is greater than delivery rate. Delivery rate is now capped by the bottleneck bandwidth. Send rate can still increase, but delivery rate is flat. The queue is building. In theory, with no active or failure-based drop, this phase still has no packet loss. From this point on, the delivery rate is limited by the network. Finally, in the buffer limited phase, the buffer fills completely. Any new data is dropped. For loss-based congestion control algorithms like Cubic or Reno, this phase is very short. It usually lasts only about one round trip time before they detect the loss and enter recovery. Its features are evenly clear. Bytes in flight exceeds BDP plus buffer. RTT reaches its maximum value. Base RTT plus the full queuing delay. Send rate is greater than delivery rate. The buffer is completely full. Packet loss is inevitable. A subtle but important detail. Because TCP relies on delayed feedback, the actual peak bytes in flight will often overshoot the BDP plus buffer line slightly. The sender doesn't know the buffer is full until the loss signal arrives, so it pushes just a little more data beyond the limit. In short, in the buffer limited phase, bytes in flight is capped at around BDP plus buffer. Loss is inevitable. This table summarizes the three phases and their characteristics. You might be wondering, how does this model help with troubleshooting? Here's the short answer. When you open Wireshark and face a screen full of packets, this model becomes your map. No matter how complex the real network is, every single transfer state can be simplified into this model. Every TCP connection, at any given moment, is in one of these three phases. There are only three ways a flow can be limited. A slow transfer always gets stuck in one of the three phases. Yes, each scenario, when examined closely, can have multiple root causes, which we'll explore later in this course. But from a transmission state perspective, there are only these three. With this model, you can instantly judge. Application limited. It's not a network bandwidth issue. Go check what's restricting the send rate. Bandwidth limited? Check if the link is saturated. Buffer limited? Not only is delivery rate capped, but loss is inevitable. Now we need to see how the congestion control algorithm reacts. The model simply tells you where the problem lives. Whenever you analyze a slow transfer, follow a simple and repeatable process. Identify the phase. Identify the limiting factor. Investigate the root cause. Implement the fix. Once you do that, troubleshooting becomes systematic instead of guesswork. For the detailed step-by-step methodology, we can't cover it all in this video. Stay tuned for future episodes. Okay, let's summarize what we've learned today. In this session, we explored how to fill the network pipe and discovered that no matter how complex a network is, a data flow, specifically its bytes in flight, can only be limited in three ways. By using Wireshark to monitor the relationship between bytes in flight, round trip time, RTT, send rate, and delivery rate, we can pinpoint exactly which phase a transfer is in at any moment. This model serves as your map for troubleshooting. Instead of guessing, you can use these signals to systematically identify the limiting factor and move straight to the root cause. All right, that's all for today. In the next episode, we'll use this network congestion model to analyze and answer a fundamental question. When does congestion actually begin? Is it when bandwidth is full? When RTT rises? Or only when packets drop? The answer changes how you see TCP forever. I'm Tai Fung, and I'll see you in the next episode.